Okay, so 13.5 covers motion in space, and so it should feel similar to problems you did back in Calc 1 where you had, you were given the acceleration, you were given an initial velocity, you were given initial position, and then you could find a position function based off of that. And so you do the same things now, it's just going to be vector versions of those things. And so let's just start with this. Okay, so we're doing the same setup. We assume we have some function that represents position. Okay, so r of t. Now this is a vector valued function, so either in the plane or in three-dimensional space, and it's just giving you the position of some particle at a given time. Then velocity is just your derivative. Is just the derivative of your position. Okay. So I guess it's not super different. Remember back when you're working before, you know your derivative's either going to, at a point, is either positive or negative, right? And so that either tells you if you're moving forwards or backwards. But now we're in three-dimensional space, or you're moving along some circle. So now, there's no forwards or backwards, right? Your position or your velocity is pointing in the direction that you're changing, and your speed is the magnitude of that velocity, right? So that's how fast you're moving, but it doesn't give you the direction, right? So velocity is both, and then acceleration is just the derivative of velocity or the second derivative of position. Okay? So that all should feel like the same setup. Oh, let's call it A. Okay, so if we're working with a problem, you see A, V, R showing up. Those should all represent those things for that example. So let's just try one here. We'll start with a relatively easy one. 2 cosine of t, 2 sine of t, t, and then find v, speed, and acceleration, all at pi over 2. And then I'm going to put in parentheses here sketch, but you might want to just hold off. I'm going to sketch it, but I don't want to, I'm just going to do a 2D sketch. So this is going to be just a spiral, right, moving up. You got that t in that last component. And so when you sketch it, let's just ignore the z. Sketch it as though you're looking straight down at the thing. And so if you get a chance, try to do that. But the first part really is just compute these derivatives and then plug in pi over 2. So again, this one should be quick, right? What's velocity? So r prime, and so in this case it's negative one, and as long as we're here, what's we want it at that specific point, so v prime at pi over 2 is what? So pi over 2 is 90 degrees, right? So sine, cosine, which ones, what are they at 90 degrees? Sine is 1 and cosine is 0.
You need the derivative or just the normal?
Oh, I didn't mean, right. Thank you. So it's just going to be negative 2, 0, 1. Is that okay? All right. And then speed is just the magnitude of that, right? And so you get square root of 4 plus 1, so 5, square root of 5. Okay? And then acceleration is just derivative of velocity, so what's that?
Minus 2 sine t minus 2 sine t.
Okay. Good. Everybody come up with that? And so evaluate that at pi over 2, and what do you end up with?
0 minus 2.
0, negative 2, 0. Good. Okay, so now I wanted to sketch this, but like I said, and I put in parentheses just to hold out for a second. What's this curve look like? 2 cosine of t, 2 sine of t. Ignore this t for a second. What's that curve?
Radius equals to 2.
Yeah, it's a circle of radius 2, right? We've seen, so x squared plus y squared is 4, right? And so you're going to get a circle of radius 2. Where do you start? When t is 0, where are you at?
2, 0.
2, 0, right? So that means if here's my x-axis, here's my y-axis, I'm starting out here at 2, 0, and then I'm going to spin around this circle of radius 2. Am I going up or down? You're going up, right? The sine will grow, so your y values are going to go up. So you're going to come around like this. I didn't even bother doing it, but what's r of pi over 2?
0 to pi over 2.
So in particular, there's where we're at, right? R of pi over 2. Now remember, we're also, so I'm calling this the x and the y-axis, so now my z-axis is coming out of the board. We're spiraling out away from there as well. I'm going to ignore that. The only place it comes in is when you look at that velocity, right? We have a little bit of velocity in that z direction then, right? 1 unit of it in that direction. So we have this. So if I now sketch my v vector, what does that look like? Negative 2, 0, 1. Again, we're just in the x, y, so we ignore the 1. So we're at that point, and we're going 2 units this way, and so that should be just like that. Does that make sense? And so again, you think of moving around a circle, right? Your tangent line should be pointing straight out there, so that's what we're finding, right? Your velocity is pointing that way, and then what about your acceleration? If we graph it, so this is v of pi over 2. 0, negative 2, so that's a vector pointing straight down 2 units, right? So from here, just down like that. Does that make sense? So this is your acceleration vector. Okay? And so that's what we're going to see in general. Your velocity vector, right, or your velocity will be parallel to your curve, and your acceleration won't necessarily be at 90 degrees, but it'll always point into where you're spinning, right? So if you're moving this way, your acceleration is always going to point into there. Sometimes it'll point something like that. In a lot of cases, it will be perpendicular, but that's not universal. Does that make sense? Okay. As long as I have this all up here, let me do this. Okay, so I'm going to repeat this problem with this function, but let me draw the picture first. So again, if I'm just in the xy plane, what's the graph of this curve? It's exactly the same, right? The 2t in the middle, just change how quickly you move around that circle. So it's exactly the same circle. When am I at t equals pi over 4? I'm at that same point, right? So t equals pi over 4, good. And so now just do the same thing. Like I said, I'll do it quickly. So r prime, what happens with those derivatives? Just an extra 2 comes out, right? So you get 4, negative 4 sine of 2t, comma, 4 cosine of 2t, comma 2, okay? Let's go ahead and do it at pi over 4. Negative 4.
Over 0.
0. Right? And then acceleration. You can do speed, I don't care about this time. Just take the magnitude. Acceleration is negative 8.
Cosine
2t.
minus 8 sine 2.
0, and so your acceleration at pi over 4 is going to be 0, negative 8, 0, right? So this time your velocity points in the same direction, but it's now 4 units long, right? And so you're moving really quickly now around that same circle, and so you should expect, if you're going quickly, your acceleration is bigger, right? You just think of driving a car around a corner, the acceleration is what you're kind of feeling, right? If you're going slowly around a corner, you don't feel much, but if you're flying around a corner, your velocity is higher, you're going to feel a much bigger acceleration, and so in this case, that acceleration is 8 units, right? So you're really way down here at negative 6. That make sense? Okay. Again, I wasn't worried about the scale there, so my scale's a little bit off. That's okay. All right, so there's one type of problem. Just kind of visualize what's happening. You're given a position. You can find these things. Most of the time we work in sort of the other direction. And so let's just start with a real generic one. Okay, so this will look like the problems you saw back in Calc 1. Find position if you knew acceleration, and so acceleration as a function this time. You also know the initial velocity, and you know the initial position. Remember back when I said we were going to be concerned or interested in integrating functions when it came to position, this is really the place where, the first place where the sort of integral of a vector valued function is going to be important. So all you have to realize, right, if acceleration is the derivative of velocity, then velocity is the integral of acceleration. So you just integrate that A, and what do you end up with? T squared I minus T squared over 2J 3T squared. Okay, right? Whatever functions are in there, you do that, and then plus some constant, that's a vector, right? And so in this case, what do we want? We want, I'm just gonna write it. That's what v of 0 is, right? The vector 1, 1, 0. If we plug 1, or we plug 0 in for t, what do we get on the right-hand side?
No.
Just the c, right? So that's your c. So your final vector for velocity is t squared plus 1, right? Because the first component of c is 1, and that's your I. And then minus, well, let me write it this way, because it's actually, it's going to be that plus 1, right? So just be careful. It's negative t squared plus 2 plus 1, j, however you want to write that. And then finally, the k is just 3t squared k, right? That make sense? And then position, you just play the game again. R is integral of velocity. So that's t cubed over 3 plus t I plus negative t cubed over 6 plus tj plus t cubed k plus c. What's your constant in this case? Yeah, right here. Position was 0, 0, 0, and so if you plug in zeros, that's what you get. And so I'm just going to do that. Leave it off. So your answer is just that without the constant. Just be careful. Make sure you find the constant if you need to. Okay? And be real careful when things like e show up, right? Because e to the 0 is 1. That always throws people off. You see, your position is supposed, or your position or velocity is supposed to be 0, 0, 0. While if e's are in the game, you might have to tweak things. Okay. I think that's probably good for there. Let's do this one. I'm just going to steal one from the book because I don't want to draw, or I don't want to write it all out. In fact, now let's do number 40. Okay. And so it says field goal, and so if you don't, well, we'll work through this. So a kicker for a football team is attempting a field goal from a distance of 40 yards. We'll come and write this stuff all down in a second. Well, let me read through the wording of this, and then we'll see what we need. From a distance 40 yards away from the goalpost, the ball is kicked from the ground with an initial speed of 65 feet per second and an initial angle of 40 degrees. Will the ball clear the goal post bar, which is 8 feet above the ground? Assume gravity is the only force acting on the object. Okay? So, let's set this up. Nope. It's annoying when stuff's on 2 different pages. So, here's the setup, right? There's the ground. It's a perfect representation of ground. You have a football, a giant football. I guess I'll draw my person. The foot is back. How's your foot look like when you're about to kick? Something like that. All right. Everybody follow the setup. So you're coming, you're going to kick the ball, there's just going to be one action on it, and then it's going to sail. And so again, it doesn't matter that it's football or that there's goalposts there. All you care, right, you're assuming he's kicking in a straight line, so that'll go over the thing. And then let's just put in our numbers. So the distance is 40 yards, so 120 feet. Okay? Is the distance from the ball to the goalpost. And what do we say, 10 feet high?
It was 8.
Is it 8? No, it says 8, or 10 here. Will the ball clear the goalpost, which is 10 feet? Is it actually 8?
No, it's 10.
It is 10.
That's realistic, I think.
Okay. All right. And then you're told that they kick at, let's just see, with an initial angle of 40 degrees, an initial speed of 65. I'm going to assume that means that that angle is 40 degrees. Does that seem reasonable? Seems like the one would measure. And then you get some velocity function here. All you know is that you're kicking with a speed, right, of 65 feet per second. Okay? All right. So, what we want to do is come up with a velocity function based off of that. So you're just going to use some trig. Right? This is a function whose length, or a vector whose magnitude is 65, right? And then you can figure out an initial velocity from there. You have initial position of, so let me write this out. So, you have an initial position of 0, 0, right? We're going to say that's our starting point. We have an initial velocity of, well, that's your first thing to find. And then you have an acceleration of, well, figure that out. So take 2 minutes, try to come up with those things. And then once you have that set up, then essentially you're doing the previous problem, right? Like we did here. But when you get to the end, you just want to know if once your x is 120 feet away, is your y still over 10 feet or not? That make sense? All right, so take a minute, try that. Remember, we're assuming everything's in some straight line, so we only have to worry about 2 dimensions yet.
What about the gravity?
Okay, so what's acceleration?
Negative 9.8.
Negative 9.8 is in meters per second. What is it in feet?
32 feet per second.
Per second squared, right? So your acceleration should be, I'll just give that to you, negative 32. Okay, you got a constant acceleration in that negative, change, sorry. We're only in 2 dimensions here, right? In the negative, so the y direction. Does that make sense? So that should be your setup. Okay, so let's just keep working here. So let me pull this vector off. I want the vector, right? Here's your point 0, 0. I want to find this vector v where this is 40 degrees and then that's 65, right?
Yeah.
So I just need to figure out the components here. Let me just write it this way. V of 0 is what? So where am I at in the x position? What's my y position?
65 cosine 40 for your x.
Okay. 65 cosine of 40 and
65 sine 40.
everyone okay with that? And you're welcome to just keep it in degrees. Just realize you're not doing any derivatives or anything, right? So you can keep those as numbers. You can punch those in. Sine and cosine of 40 aren't values that we have nice, numbers for. So I would just leave them like this for now. Okay, so that's your initial velocity. Okay? And so now we just start marching through this problem. So if acceleration is negative, I'll just write it in the form we had before, 0, negative 32, right? Then what is velocity? 0, negative 32t plus some constant, right? And now what is that constant? Well, it should be whatever you get over there, right? When you plug in 0, this is all gone. Oops. So let's just write it out. So that's 60 cosine of 40, comma, oh, is it 65?
Yeah.
65 sine of 40, right? That's your velocity at time 0, and your velocity at time 0 is just that c, right? So those will get plugged in. So all you're going to do is plug that in for c, and so it'll just get added. So your final, or your next line will be that you get 65 cosine of 40 t, or not t yet, jumping ahead, comma, negative 32t plus 65 sine of 40. Does that make sense? Okay, now what is acceleration? Position, r. Integrate that, what do you get? 65. T, right? It's just a constant. You integrate that, you just get that times t, and then minus, you get 16 e squared plus 65 sine of 40 t, right? And again, I think I'll skip plus a constant. What's the constant? It's going to be 0, right? Because you plug 0 into this, everything's gone, and your initial point was 0. So there's your position function right there. The book basically comes up with this position function for a generic situation like this, where you're shooting it along some vector. If you want to try to memorize that, I guess I'm not going to complain, but it's so easy to just come up with it really quick, right? And even after you've done a couple of these, you almost skip this step and just say, okay, I know it's negative 32t, and then I add on my, my v, and then you integrate, you just tack on t's. And if you have a change in it, if your initial position isn't at your 0, 0, then you might have to do something else. But I really don't think it's worth memorizing an extra formula, because if you screw it up, it throws out the whole problem. Okay, so now we're at the point where we need to figure out, right, this ball comes, does it clear this goalpost or not? So how do we do that?
So for your x, you have 120, and for your y, you have 10.
Right, and so it's not that you can set them both equal to that, but the question is, when your x is 120, is your y above or below 10, right? That's what you're looking for. So find the time when x equals 120, so that's just 120 equals your 65, right, cosine of 40 times t, so your t is 120 divided by 65 cosine of 40. That makes sense? And then plug that into your y. Plug into y. The y of that. Let's call this time t naught. Actually, it's not. That's fine. Let's call it t1. t1. And so y at that time, right, is just negative 16 t1 squared plus 65 sine of 40 times t1. And I would would say this is a place where the reasonable approach is to just punch this in your calculator now, just make sure you're in degree mode, and you end up with 120 divided by 64. Oops, 40. Negative 16 x squared plus 55 sine. All right, so now I screwed that up the first time. All right, so double check for me, because I screwed it up once already, but I was getting about 7.6, so 7.76 feet. And so what's our conclusion?
Oh, no, it doesn't make it.
So it won't make it over the 10 foot, so that. Just. Does that make sense? And so this should hold anytime you have some kind of projectile where you're just spitting it out. Did you get a different number? Or you giving me a face where you look unhappy with it?
I just don't know anything about football.
Okay, so you don't need to know anything. This is all you need to know. Think of it as a soccer ball, right? And you're trying to kick it over some fence, right? All we need to know is you got a ball, it's going in this direction, will it clear this 10-foot fence over here? I mean, it's a goalpost, but it's enough just to think of it as a fence. And so-
Because it's less than 10, like you said that.
Right, so what we've seen, right, is that when your distance is 120, your time is this number, okay?
Yep.
So that means this ball is just, for every time, it's got one X and one Y value, right? And so we've found when we get to 120 in my X direction, I'm at T1. So my X value is T1, so X of T1 is 120. And then what's Y of T1? 7.763. That's somewhere around there. So are we going over this thing? No, our ball's coming like this, and it's on its way down there. It's not going to clear that 10-foot thing. If that number was 12, then we would have cleared the fence. Or cleared the goalpost. Does that make sense? So don't get too bogged down in what the actual objects are. You're just thinking, you got a projectile, will it make it over whatever the height is on the other side? Okay? All right. Okay, so let's stop there. I'll have you try homework. I'm sure there'll be some questions, so just bring those next time. But we'll go